In previous episodes, we explored foundational work in four groundbreaking fields: Einstein's general relativity, quantum mechanics, quantum biology, and chaos theory with emergence. This raises a fundamental question. Could subatomic processes drive emergent phenomena that shape our universe, and even life itself? Furthermore, if multiple universes exist, why do we inhabit this particular one, and how did life begin here? Today we'll examine two profound scientific questions. How unlikely is our universe's existence, and what are the odds that life could emerge within it? We'll start with the concept of a fine-tuned universe. This idea suggests that the fundamental physical constants, those seemingly arbitrary numbers governing how our universe operates, are precisely calibrated for complexity. Even a tiny change in values like the fine structure constant would create a universe unable to support stars, complex structures, or life itself. To give us a sense of the historical context, let's spotlight Sir Fred Hoyle. He famously worked on how elements form within stars. His insights, along with the groundbreaking B2FH paper of 1957, showed how heavier atoms like carbon and oxygen emerge from nuclear fusion in stellar interiors. Moving on, the physicist Richard Feynman also had a deep fascination with these constants. He described the fine structure constant as one of the greatest damn mysteries of physics. In his work on quantum electrodynamics, Feynman illustrated just how delicate these universal numbers are. Numerous publications, QED, The Strange Theory of Light and Matter, The Character of Physical Law, and the Feynman Lectures on Physics, offer glimpses into how these constants both fit into and remain puzzling outliers of our mathematical understanding of nature. Cosmologist Martin Rees, Astronomer Royal, former Master of Trinity College, and President of the Royal Society, has discussed the fine-tuned universe extensively. In works such as Cosmic Coincidences, Just Six Numbers, and Our Cosmic Habitat, Rees explains how only a careful balance of cosmic parameters allows for the emergence of galaxies, stars, planets, and ultimately life. His 6 key cosmic numbers each appear meticulously set, suggesting that if they were dialed differently, we would not be here to wonder about it at all. Likewise, Stephen Hawking and his collaborator Thomas Hertog wrestled with notions of cosmic fine-tuning. In books like The Grand Design and A Brief History of Time, Hawking proposes that a vast multiverse might contain a range of pocket universes with varied laws of physics, and only in those that are just right for life do observers appear. These different approaches lead us to several theoretical answers. The anthropic principle claims that we naturally find ourselves in a universe suited for life, because only in such universes can observers exist. The multiverse hypothesis suggests many possible universes, each with varying constants, and we inhabit one of the lucky ones. Or perhaps future naturalness arguments will provide a framework in which these parameters are less mysterious. Having established that our universe seems fine-tuned for life, the next logical question is, how did life itself gain a foothold? We'll step back in time to the Miller-Urey experiment of 1952, which demonstrated that organic molecules, amino acids, could form under conditions simulating the primitive Earth's atmosphere. Sidney Fox, a few years later, showed how heating certain amino acid solutions could create more complex, protein-like structures. Fast forward to more modern research, such as the Lincoln and Joyce experiment, demonstrating an RNA-based system capable of replicating, evolving, and undergoing Darwinian selection, all without needing proteins or cells. This groundbreaking work points toward RNA's potential as an early self-replicator. And then there's assembly theory, a new framework that treats every observable object as the product of a specific set of building steps, helping us understand how ever more novel features appear through selection and history, both in biology and physics. So where does this leave us? We've seen how the universe's constants appear exquisitely tuned for complexity, and we've explored the early scientific efforts to understand how life began in a seemingly improbable arena. In our next episode, we'll confront that very temptation to wonder whether, among the vast space of possible universes, ours is uniquely primed not only for physical existence, but also for life, and what that might reveal about our deepest understanding of reality. Thank you for joining me on this journey, and I look forward to continuing our exploration next time.